Tonight I want to tell you a story about three men who changed the shape of the universe. Not the actual shape, the universe didn't care what they thought, the model. The picture we carry around of where we are, what moves, what stays still, and why any of it matters. The story spans about 150 years, from the middle of the 1500s to the end of the 1600s, and it involves a Danish nobleman who lost his nose in a sword fight over a mathematical formula, a German mystic who believed the planets made music as they orbited, and an English recluse who invented a new kind of mathematics just to describe how apples fall and moons orbit, and then almost didn't bother to tell anyone about it. These three men, Tycho Brahe, Johannes Kepler, and Isaac Newton, are the reason we understand how planets move, not in a vague poetic sense, in a precise, predictive, mathematical sense. The kind of understanding that lets you launch a spacecraft from Florida and land it on a specific crater on Mars 9 months later. That understanding didn't exist before these three men. After them, it did. And the way it came into existence is one of the strangest, most human, most improbable stories in the history of science. But before I tell you their story, I need to tell you what the world looked like before them. Because you can't appreciate what they built unless you understand what they had to tear down first. For most of human history, the Earth was the center of everything, not in a metaphorical sense, literally. The Earth sat motionless at the center of the cosmos, and everything else, the sun, the moon, the planets, the stars, revolved around it. This wasn't stupidity, it was observation. If you go outside tonight and watch the sky, that's exactly what you'll see. The stars wheel overhead from east to west. The sun rises, arcs across the sky and sets. The moon drifts through the constellations. Everything moves, the ground beneath your feet does not. The geocentric model, Earth at the center, is what the sky actually looks like from the surface of the Earth. It took extraordinary intellectual courage to argue otherwise, because arguing otherwise meant telling people that their direct sensory experience was wrong. The most sophisticated version of the geocentric model was built by Claudius Ptolemy, a Greek-Egyptian astronomer working in Alexandria around 150 AD. Ptolemy's system was a masterpiece of geometric ingenuity. He placed the Earth at the center, surrounded by concentric spheres carrying the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the fixed stars. But the planets didn't just move in simple circles. They did something weird. If you watch Mars over the course of several months, plotting its position against the background stars night after night, you'll see something peculiar. Mars generally moves eastward through the constellations, but periodically it slows down, stops, reverses direction, and moves westward for a few weeks, stops again, and then resumes its eastward motion. This backward movement is called retrograde motion, and every planet visible to the naked eye does it. Retrograde motion is incredibly difficult to explain if you believe the planets orbit the Earth in simple circles. Ptolemy's solution was epicycles, small circles riding on larger circles. Each planet didn't just orbit the Earth. It orbited a point that orbited the Earth. And that point didn't sit at the center of the larger circle either. Ptolemy introduced the concept of the equant, an offset point from which the angular motion of the planet appeared uniform. The geometry was complex, nested, and frankly beautiful in its intricacy, and it worked. Ptolemy's model could predict planetary positions with reasonable accuracy. Not perfect accuracy, errors of a degree or two were common, and over centuries those errors accumulated, but for practical purposes like calendar keeping, astrology, and navigation, Ptolemy was good enough. His model dominated Western and Islamic astronomy for 1400 years. That's an extraordinary run for any scientific theory. But there were cracks. Astronomers throughout the medieval period noticed that Ptolemy's predictions slowly drifted away from observation. They patched the model, adding more epicycles, adjusting parameters, but the patches made the system increasingly unwieldy. By the late Middle Ages, the Ptolemaic model had become a contraption of dozens of interlocking circles, each one added to fix a discrepancy that the previous circles hadn't quite resolved. It worked in the sense that a machine with enough gears can approximate almost any motion. But it had lost any claim to elegance, and some astronomers began to suspect it had lost its claim to truth. Alfonso X of Castile, a 13th century king who sponsored the creation of astronomical tables based on Ptolemy's model, reportedly said that if God had consulted him during the creation, he would have recommended something simpler. That story is probably apocryphal, but the sentiment was real. Ptolemy's system predicted, it did not explain. And as the centuries wore on, the gap between prediction and explanation became harder to ignore. Then in 1543, a Polish canon named Nicolaus Copernicus published a book that rearranged the cosmos, Copernicus's De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, proposed that the Sun, not the Earth, sat at the center of the planetary system. The Earth was just another planet orbiting the Sun, along with Mercury, Venus, Mars, Jupiter, and Saturn. The Moon alone orbited the Earth. The stars were distant, fixed, immovable. This was not entirely original. Aristarchus of Samos had proposed a heliocentric model in the 3rd century BC, but Aristarchus's idea had been rejected, partly because it contradicted common sense and partly because it predicted stellar parallax, a slight shifting of stellar positions that should be visible if the Earth moves. No such parallax had been observed. The ancient astronomers concluded, logically enough, that the Earth must be stationary. What they didn't consider, what Copernicus himself only vaguely appreciated, was that the stars might be so incredibly distant that the parallax was too small to detect with the naked eye, and that turned out to be the case. Stellar parallax was finally measured in 1838, nearly 3 centuries after Copernicus, using telescopes far more precise than anything available in the 16th century. The nearest stars showed a parallax of about 1 arcsecond, 1/3600th of a degree. No wonder the ancients couldn't see it. Copernicus's model had a beautiful feature. Retrograde motion, that maddening backward loop of Mars and the other planets, was explained naturally without epicycles. It was simply a consequence of the Earth overtaking a slower outer planet on a smaller, faster orbit. When you pass a car on the highway, the other car appears to move backward against the distant landscape, even though both cars are moving forward. The same geometric effect explains retrograde motion if both the Earth and Mars orbit the Sun. But Copernicus's model also had a problem, he insisted, as Ptolemy had, that planetary orbits were perfect circles, and they're not. Orbits are ellipses. Because Copernicus used circular orbits, his predictions were no more accurate than Ptolemy's. In some cases, they were worse. Copernicus himself had to reintroduce epicycles, smaller ones than Ptolemy's, but epicycles nonetheless, to make his circular orbits match the observed positions of the planets. So Copernicus had the right basic idea, the Sun at the center, but the wrong geometry circles instead of ellipses. His model was philosophically revolutionary but practically mediocre. It could not on its own replace Ptolemy. To do that, you needed better data. And to get better data, you needed someone obsessed enough, wealthy enough, and stubborn enough to spend decades staring at the sky and writing down what they saw with unprecedented precision. You needed Tycho Brahe. Tycho Brahe was born on December 14, 1546 in Scania, which was then part of the Kingdom of Denmark and is now the southernmost region of Sweden. He was born into one of the most powerful noble families in Denmark. The Brahes were among the highest-ranking aristocrats in the kingdom, with vast estates, political influence, and a tradition of military and diplomatic service. But Tycho wasn't raised by his parents. Shortly after his birth, the exact circumstances are disputed. He was taken by his uncle Jörgen Brahe, who was childless and wealthy. Jörgen essentially adopted Tycho, raising him on his own estate and providing him with an education befitting a nobleman. The arrangement was apparently made without his parents' full consent, and the dynamics of this unusual family situation seem to have shaped Tycho's personality in lasting ways. He grew up knowing he was wanted enough to be taken, but also knowing that his life had been redirected from its expected course before he was old enough to object. The event that changed Tycho's life, the event that turned a Danish nobleman into an astronomer, happened on August 21st, 1560, when Tycho was 13 years old. A solar eclipse occurred, and it had been predicted. This seems unremarkable to us. We predict eclipses routinely and with extraordinary precision, but to the young Tycho it was a revelation. Human beings could know in advance what the sky would do. The heavens were not inscrutable, they followed rules. And those rules could be discovered, codified, and used to predict the future. Tycho later wrote that this moment, the realization that celestial events were predictable, filled him with what he described as something close to divine wonder. He decided then and there that he would devote his life to astronomy. His family was horrified. Astronomy was not a suitable pursuit for a nobleman. Noblemen fought wars, managed estates, served the king. They did not sit in cold towers staring at stars. Tycho studied at the University of Copenhagen and later at universities in Leipzig, Wittenberg, Rostock, Basel, and Augsburg. His family wanted him to study law and prepare for a diplomatic career. Tycho endured the law lectures and spent every clear night making astronomical observations. He was, by his own later account, a mediocre law student and an exceptional amateur astronomer. It was in Rostock in December 1566 that Tycho lost part of his nose. The circumstances tell you everything about his personality. In the dark of a December evening, swords were drawn, and Parsberg's blade cut through the bridge of Tycho's nose, removing a significant portion of it. For the rest of his life, Tycho wore a prosthetic nose. Contemporary accounts describe it as made of metal, traditionally said to be gold and silver, though copper alloy is more likely for daily wear. When his body was exhumed in 2010, chemical analysis of his skull showed traces of copper and zinc around the nasal area, consistent with a brass prosthesis. He apparently had multiple prostheses, perhaps a lighter one for daily use and a more ornate one for formal occasions. The nose became part of his legend, a man who had literally put his face on the line in defense of his mathematical honor. It's the kind of detail that makes you realize these were not the austere marble bust figures that history textbooks suggest. They were passionate, volatile, sometimes absurd human beings who happened to transform our understanding of reality. In November 1572, something happened that made Tycho Brahe famous across Europe. A new star appeared in the constellation Cassiopeia. Not a comet, not a meteor. A star, brilliant, bright enough to be visible in daylight for several weeks, gradually fading over the following months until it disappeared about 16 months later. We now know this was a supernova, a type EAA supernova to be precise, the thermonuclear detonation of a white dwarf star about 9,000 light-years from Earth. It's now catalogued as SN157T2 or Tycho's supernova. The remnant is still visible to modern telescopes as an expanding shell of hot gas. But in 1572, nobody knew what a supernova was. The word didn't exist. And the appearance of a new star was not just astronomically interesting, it was philosophically explosive. The Aristotelian worldview, which had dominated European thought for nearly 2,000 years, held that the heavens were perfect and unchanging. Change, birth, death, corruption, creation happened only in the sublunary realm, below the moon. The celestial spheres beyond the moon were made of a perfect, incorruptible fifth element, the quintessence, and they did not change ever. A new star in the heavens was a direct contradiction of this doctrine. If the heavens could change, then they weren't perfect and immutable. And if they weren't perfect and immutable, then the entire Aristotelian framework for understanding the cosmos was in trouble. But was the new star really in the heavens? Could it perhaps be an atmospheric phenomenon, something in the Earth's atmosphere that merely looked like a star? This was the question that everything hinged on, and it was a question that could be answered by measurement. If the new star was close in the atmosphere, or even between the Earth and the Moon, then it should show parallax. That is, its position relative to the background stars should shift as the Earth rotated or as the observer moved to different locations. The closer the object, the larger the parallax. Tycho set out to measure this parallax with every instrument he had. He found none, zero. The new star showed no detectable parallax at all. It was fixed against the background stars to within the precision of his instruments, which, as we'll discuss, was the best precision available anywhere in the world. The conclusion was inescapable. The new star was far beyond the Moon, in the supposedly unchanging realm of the fixed stars. Tycho published his findings in a book titled De Nova Stella, on the new star, in 1573. The title itself was revolutionary: Nova Stella, a new star, two words that contradicted 2 millennia of cosmological orthodoxy. The book made Tycho famous. It also brought him to the attention of King Frederick II of Denmark, who saw an opportunity to enhance Denmark's prestige by supporting its most famous scientist. In 1576, Frederick made Tycho an extraordinary offer: the island of heaven in the strait between Denmark and Sweden, along with funding to build whatever he needed. What Tycho built on heaven was unprecedented. He called it Uraniborg, Castle of Urania, named after the muse of astronomy. It was not simply an observatory, it was a research campus, a palace of science. Uraniborg was a Renaissance chateau equipped with the most precise astronomical instruments ever constructed. Tycho designed them himself: enormous quadrants, sextants, armillary spheres, and azimuthal instruments built to specifications that pushed the limits of what 16th century metalwork could achieve. The instruments were made of brass and iron with carefully graduated scales that could be read to fractions of an arcminute. No telescopes. This is the crucial point that most people miss. Tycho Brahe did all of his work with the naked eye. The telescope wouldn't be applied to astronomy until 1609, 8 years after Tycho's death. Every measurement, every observation, every data point in Tycho's vast catalogue was obtained by sighting along metal instruments and reading graduated scales in candlelight or moonlight. And yet his measurements were accurate to about 1 to 2 arcminutes, roughly 1/30th of a degree. This might not sound impressive in an era when telescopic measurements can achieve accuracy of fractions of an arcsecond, but for naked eye observation, Tycho's precision was about 20 times better than any of his predecessors. He achieved this through a combination of superior instruments, meticulous technique, systematic error correction, and sheer, relentless dedication. He observed not occasionally but nightly, weather permitting, for more than 2 decades. He didn't take a few measurements and move on. He measured the same objects repeatedly, averaged the results, and tracked any systematic trends that might indicate instrument error. He also built a second underground observatory called Stjerneborg Star Castle, adjacent to Uraniborg. The underground location protected the instruments from wind vibration, which Tycho had identified as a significant source of measurement error. Think about that level of obsessiveness. He noticed that wind shaking his instruments was degrading his data by a fraction of an arcminute. so he built an entire underground facility to eliminate it. For 20 years, from 1576 to 1597, Tycho observed the heavens from heaven. He catalogued the positions of over 700 stars, measured with a precision that wouldn't be substantially surpassed until telescopic observations became routine. He tracked the motions of the planets, Mars in particular, with a consistency and accuracy that nobody had ever achieved. The Mars data would turn out to be the key, not for Tycho, for someone else. But we'll get to that. Tycho's personal life on Hiven was as extraordinary as his scientific work. He ruled the island like a feudal lord because he essentially was one. He had been granted the island and its revenues by the king, and he treated the local peasants as his subject. He imposed labor requirements, collected taxes, and wasn't above imprisoning anyone who defied his authority. The islanders resented him. Complaints about Tycho's tyrannical behavior eventually reached the Danish court, and they contributed to his later downfall. He lived in astonishing opulence for a scientist. Uraniborg had running water, one of the first buildings in Scandinavia to have indoor plumbing. It had a chemical laboratory in the basement, where Tycho practiced alchemy alongside his astronomy. It had a printing press, so he could publish his own works without depending on distant publishers. It had gardens designed with geometric precision, reflecting his belief in the mathematical harmony of nature. He kept a pet moose. This is not a metaphor. He had an actual moose, an elk, in European terminology, that wandered the halls of Uraniborg. The moose reportedly died after drinking too much beer at a nobleman's dinner party and falling down the stairs. This is attested in Tycho's own correspondence. You cannot invent details like this. He also employed a dwarf named Jep, who sat under the dinner table during meals and was believed by Tycho to have psychic abilities. The household included a rotating cast of students, assistants, visiting scholars, family members and servants, all orbiting around Tycho's enormous personality like planets around a particularly eccentric sun, and he had a relationship that defied the social norms of his time. Tycho lived with a woman named Kirsten Jorgenstatter, who was a commoner. Under Danish law, a nobleman who married a commoner would lose his noble status and his lands. Tycho and Kirsten never formally married, but they lived together for nearly 30 years and had 8 children. Their relationship was what Danish law called a left-handed marriage, legally recognized but without conferring noble status on the spouse or children. Tycho's children could not inherit his titles or his noble privileges. This must have been a source of constant tension, both within the family and in Tycho's relations with other nobles who viewed the arrangement as beneath his station. But none of this, not the moose, not the nose, not the dwarf, not the common law wife, would matter to history, if not for the data. The data was everything. 20 years of planetary observations, the most precise in history, recorded in meticulous tables that specified the positions of the planets night after night, month after month, year after year. And it was this data, specifically the Mars data, that would enable the next step in the story. But first, Tycho had to fall. In 1588, King Frederick II died. His successor, Christian IV, was initially supportive of Tycho, but the relationship deteriorated. Tycho was expensive. Uraniborg consumed roughly 1% of Denmark's entire state budget. He was arrogant, demanding, and politically tone-deaf. He alienated courtiers, argued with ministers, and showed an aristocrat's contempt for anyone who questioned his prerogatives. The complaints from Asien's peasants didn't help. By 1597, Tycho's funding had been cut, his political protectors had withdrawn their support, and his position in Denmark had become untenable. He left heaven, taking his instruments, his records, his family, and probably his moose. Actually, the moose was already dead by then, and spent 2 years wandering through northern Europe, looking for a new patron. He found one in 1599, Rudolf II, the Holy Roman Emperor, who held court in Prague. Rudolf was a fascinating figure, an obsessive collector of art, curiosities and knowledge, who presided over one of the most intellectually vibrant courts in Europe while his empire slowly crumbled around him. Rudolf offered Tycho a castle near Prague, a generous salary and the title of imperial mathematician. Tycho accepted. It was in Prague, in the last 2 years of his life, that Tycho made the decision that would define the future of astronomy. He hired an assistant, a young, brilliant, difficult, impoverished German mathematician named Johannes Kepler. Kepler was born on December 27, 1571 in Wilderstadt, a small town in the Duchy of Württemberg in what is now southwestern Germany. If Tycho Brahe was born into privilege and chose astronomy despite his family's objections, Kepler was born into misery and arrived at astronomy through a combination of intellectual brilliance, desperate ambition, and what he believed was divine guidance. His father, Heinrich Kepler, was a mercenary soldier who was absent for most of Kepler's childhood and eventually disappeared entirely, probably killed in a war in the Netherlands. His mother, Katharina, was a difficult woman who was later accused of witchcraft, an accusation that Kepler himself would spend years fighting to defend against at enormous personal cost. His childhood was marked by illness, poverty, and the chaos of a family in constant crisis. Kepler was sickly from birth. He had severe myopia, nearsightedness so extreme that detailed astronomical observation was essentially impossible for him. He also suffered from crippled hands, possibly a result of smallpox that limited his manual dexterity. The irony is extraordinary. The man who would discover the laws of planetary motion could barely see the planets and couldn't have operated Tycho's instruments if his life depended on it. What Kepler had was a mind of staggering mathematical ability and an almost mystical conviction that the universe was constructed according to mathematical principles. He believed with a fervor that bordered on religious ecstasy that God was a mathematician and that the structure of the cosmos reflected divine geometry. This belief drove him to search for mathematical patterns in everything, and while many of his searches led to dead ends and nonsense, a few of them led to the most profound discoveries in the history of science. Kepler's first book, Mysterium Cosmographicum, The Cosmographic Mystery, published in 1596, illustrates both his brilliance and his tendency toward beautiful but wrong ideas. Kepler asked why there were exactly 6 planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, and why they were spaced the way they were. His answer, the 5 regular solids, the Platonic solids, could be nested between the 6 planetary orbits, one solid between each pair of adjacent orbits, and the resulting geometry approximately matched the observed spacing. A cube between Saturn and Jupiter, a tetrahedron between Jupiter and Mars, a dodecahedron between Mars and Earth, an icosahedron between Earth and Venus, an octahedron between Venus and Mercury, nested inside each other with the planetary orbits inscribed and circumscribed on the faces of each solid. It's a gorgeous idea. It's completely wrong. The spacing of the planets has nothing to do with Platonic solids, and of course there are more than 6 planets. Kepler didn't know about Uranus, Neptune, or the dwarf planets. But the fact that the model approximately worked for the known planets gave Kepler enough encouragement to continue. And the book, despite its flawed premise, demonstrated mathematical sophistication that caught the attention of 2 important people, Tycho Brahe and Galileo Galilei. Galileo wrote Kepler a polite letter acknowledging receipt of the book, but not engaging deeply with its contents. The 2 never developed a close working relationship, which is one of the great missed opportunities of scientific history. They were contemporaries. They were both Copernicans and they were both geniuses, but they worked in very different ways. Galileo was an experimentalist and observer. Kepler was a theoretician and calculator, and they never found a way to combine their strengths. Tycho's reaction was more consequential. He recognized Kepler's mathematical talent and saw in him a potential collaborator, someone who could take Tycho's observational data and extract mathematical patterns from it. This was something Tycho himself was not equipped to do. Tycho was the greatest observational astronomer in history, but he was not a great mathematician. He could measure the position of Mars to 1 arcminute, but he couldn't figure out the mathematical law that governed that position. For that, he needed someone like Kepler. In 1600, Tycho invited Kepler to join him in Prague. Kepler, who was struggling financially and professionally, he had been working as a mathematics teacher in Graz, a position he found stifling, accepted. The relationship between Tycho and Kepler is one of the great dramas of scientific history, and it was fraught from the beginning. They were very different men. Tycho was wealthy, aristocratic, flamboyant, and used to command. Kepler was poor, bourgeois, intense, and used to being underestimated. Tycho was generous with hospitality, but secretive with data. Kepler was obsessive about data and indifferent to hospitality. The central tension was the data. Kepler wanted full access to Tycho's observational records, the 20 years of planetary positions that represented the most valuable astronomical data set in the world. Tycho was reluctant to give it. He doled out data in small portions, assigning Kepler specific problems to work on, but withholding the complete picture. Tycho's reasons were partly professional and partly personal. Professionally, he wanted to ensure that the data would be used to support his own cosmological model, a compromise system called the Tychonic model, in which the planets orbited the Sun, but the Sun orbited the Earth. This model preserved Earth's immobility while accepting the mathematical convenience of sun-centered planetary orbits. It was observationally indistinguishable from Copernicus's model for most purposes, and Tycho considered it his most important intellectual achievement. Personally, Tycho seems to have been wary of Kepler's ambition and intellect. He recognized that Kepler was in some ways smarter than he was, at least mathematically, and he may have worried that giving Kepler unrestricted access to the data would result in Kepler publishing results under his own name without adequate credit to the man who had spent decades collecting the observations. This was not an unreasonable concern. In the 16th century, there was no system of academic citation or shared credit. Scientific priority was a zero-sum game. The two men argued frequently. Kepler complained in letters to friends that Tycho was withholding data and treating him as a servant rather than a colleague. Tycho complained that Kepler was impatient, ungrateful, and insufficiently respectful of his elder's achievements. At one point, Kepler left Prague in a fit of anger, only to return weeks later after apologizing. The specific task Tycho assigned to Kepler was the orbit of Mars. This was either a stroke of genius or a stroke of extraordinary luck, depending on how much foresight you attribute to Tycho. Mars has the most eccentric orbit of any planet visible to the naked eye, except Mercury. Its orbit is an ellipse with an eccentricity of about 0.093, meaning it deviates from a perfect circle by a few percent. This might not sound like much, but it was enough to produce discrepancies of up to 8 arcminutes between a circular orbit and the observed positions. 8 arcminutes, about a quarter of the Moon's apparent diameter. Tycho's data was accurate to 1 or 2 arcminutes, so the 8 arcminute discrepancy was not noise, it was signal. If Tycho's instruments had been less precise, if the error margin had been 10 arcminutes instead of 2, the discrepancy would have been lost in the measurement uncertainty. Kepler would have fitted a circular orbit and moved on. The laws of planetary motion might not have been discovered for decades or centuries. This is one of the most consequential coincidences in the history of science. Tycho's instruments were just barely good enough to reveal the elliptical nature of planetary orbits. A generation earlier, the data wouldn't have been precise enough. A generation later, telescopes would have made the measurement trivial. But in that specific window, the late 1500s, with Tycho's naked eye instruments pushed to their absolute limit, the data was precise enough to show that circular orbits didn't work, but not so overwhelming that the answer was obvious. It required someone of Kepler's mathematical ability to tease the answer out, and then Tycho died on October 13, 1601. Tycho attended a banquet in Prague. According to Kepler's account, Tycho drank extensively but refused to leave the table to relieve himself, considering it a breach of etiquette. He fell ill shortly after the dinner with a bladder or kidney complaint. Over the next 11 days his condition deteriorated, and on October 24, 1601 he died. He was 54 years old. The cause of death has been debated for centuries. The traditional explanation is a bladder infection, possibly complicated by uremia, a toxic buildup of waste products in the blood due to kidney failure. For a time there was speculation that Tycho had been poisoned with mercury, possibly by Kepler himself, who had the most to gain from Tycho's death and immediate access to his data. When Tycho's body was exhumed in 2010, hair and bone samples were analyzed for mercury. The results showed elevated but not lethal levels of mercury, consistent with Tycho's known alchemical work rather than poisoning. The current consensus is that Tycho died of natural causes, most likely related to kidney failure, but the death, however it occurred, was transformative for Kepler. 2 days before dying, Tycho reportedly asked Kepler to complete his work and, crucially, to use the Tychonic model rather than the Copernican one. The deathbed request, if it happened as described, has an almost Shakespearean quality, the dying master extracting a promise from his successor, a promise the successor has no intention of keeping. Within days of Tycho's death, Kepler secured access to the complete observational records. The exact circumstances of this acquisition are disputed. Some historians suggest Kepler simply took the data, that he seized the records before Tycho's heirs could claim them. Others argue that Kepler was appointed by Emperor Rudolf as Tycho's successor as imperial mathematician, and that access to the data came with the position. The truth probably involves elements of both. Kepler was aggressive, ambitious, and fully aware that the data was the most valuable scientific resource in the world. He was not going to let it slip away because of legal niceties. And so Kepler, at the age of 29, found himself in possession of something no one else had ever had, a comprehensive, high-precision record of planetary positions spanning 2 decades. The question now was what to do with it. What he did with it took 8 years. Kepler began by trying to fit Mars's orbit to a circle. This was the natural starting point. Every astronomer since antiquity had assumed that celestial orbits were circular, circles were perfect. The heavens were the realm of perfection. Orbits must be circles. Kepler tried. He tried for years. He tried every variation of circular orbits he could think of. Circles with displaced centers, circles with equants, combinations of circles. He calculated literally thousands of possible configurations. Each time he compared his predictions with Tycho's observations, and each time he found discrepancies. The discrepancies were small, 8 arcminutes at most. If Kepler had been working with anyone else's data accurate to 10 or 15 arcminutes, he could have declared success and moved on. But he was working with Tycho's data, and Tycho's data was accurate to 2 arcminutes or better. An 8 arcminute error was 4 times larger than the measurement uncertainty. It was not acceptable. Here is where Kepler made the decision that separates him from every astronomer who came before. He trusted the data more than the theory. He wrote in his monumental work Astronomia Nova that these 8 arcminutes could not be ignored, because divine goodness has given us in Tycho Brahe a most diligent observer from whose observations this 8-minute error of Ptolemy's is deduced. The data said circles were wrong. Therefore, circles were wrong. Do you understand how radical this was? For 2,000 years, since Plato, since Aristotle, since the Pythagoreans, circular motion had been considered the only kind of motion worthy of the heavens. To abandon circles was not just a mathematical adjustment, it was a philosophical revolution. Kepler was saying that the ancient assumption of celestial perfection was wrong, that the actual behavior of the planets, messy, elliptical, non-circular, was more important than any philosophical ideal. He was choosing reality over beauty. Or rather, he was redefining beauty to mean whatever reality actually was. So if not circles, then what? Kepler tried ovals, he tried egg shapes, he tried various curves generated by combinations of circular motions. He computed, he compared, he discarded. He tried again. The answer, when it finally came, was an ellipse, a specific kind of ellipse, one with the sun at one focus. An ellipse is a closed curve defined by two special points called foci. For any point on the ellipse, the sum of the distances to the two foci is constant. If the two foci coincide, the ellipse becomes a circle. The more separated the foci are, the more elongated the ellipse. Kepler found that Mars's orbit was an ellipse with the sun at one of the two foci, not at the center of the ellipse at one focus. The other focus was an empty point in space with nothing there. This was his first law. All planets move in elliptical orbits with the sun at one focus. The second law came from his analysis of Mars's speed along its orbit. Kepler noticed that Mars moved faster when it was closer to the sun and slower when it was farther away. He quantified this by discovering that the line connecting a planet to the sun sweeps out equal areas in equal time. In other words, if you draw a line from the sun to Mars and you let Mars move for say 30 days, the area of the pie-shaped region swept out by that line is the same whether Mars is close to the sun, moving fast, or far from the sun, moving slowly. The shape of the region changes, narrow and long when Mars is close, wide and short when Mars is far, but the area is the same. This is the law of equal areas. It's a precise quantitative statement about how planetary speed varies with distance from the sun. And it fell directly out of Tycho's data, because the data was precise enough to reveal the speed variations. Kepler published these two laws in 1609 in Astronomia Nova, New Astronomy. The full title is gloriously long and tells you everything about Kepler's personality. Astronomia Nova etiologetos, so physica coelestis, tradita commentaris de motibus stellae Martis, ex observationibus GV. Tychonis Brahe, translated roughly, new astronomy based upon causes or celestial physics, treated by means of commentaries on the motions of the star Mars, from the observations of the noble Tycho Brahe. He credited Tycho. He had to. The data was Tycho's, but the insight was Kepler's. The equal area law was Kepler's. The willingness to throw away 2,000 years of circular orthodoxy was Kepler's. The third law came later. 9 years later, in 1618, Kepler discovered a mathematical relationship between a planet's orbital period, how long it takes to go around the sun, and its average distance from the sun. Specifically, the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. In mathematical notation, t squared is proportional to a rub, where t is the period and a is the semi-major axis, essentially the average orbital radius. This law connects all the planets to each other. It says that the solar system is not a random collection of orbits. It's a system with a single underlying mathematical structure. If you know a planet's distance from the sun, you can calculate its orbital period. If you know its period, you can calculate its distance. One number gives you the other through a simple mathematical relationship. Kepler published the third law in 1619 in Harmonices Mundi, the harmony of the world. This book is a strange, sprawling work that mixes rigorous mathematics with mystical speculation about the musical harmonies produced by the planets. Kepler calculated the angular velocities of each planet at its closest and farthest points from the Sun, expressed them as musical intervals, and argued that the planets literally played music, the music of the spheres, as they orbited. Saturn, the slowest planet, sang bass. Mercury, the fastest, sang soprano. The Earth song varied between two notes, Mi and Fe, which Kepler interpreted as representing misery and famine. This is the part of Kepler that makes modern scientists uncomfortable. The same mind that discovered the elliptical orbit law also believed the planets made music. The same mathematical rigor that produced the area law also produced elaborate numerological speculations that led nowhere. Kepler did not distinguish between his correct insights and his incorrect ones, at least not in the way we would. He pursued all of them with the same intensity, the same conviction, and the same mathematical precision. The universe for Kepler was a single harmonious whole, and every pattern he found, whether real or imagined, was a glimpse of divine design. This raises a fascinating question about the nature of scientific genius. Was Kepler's mysticism a distraction from his science, or was it the fuel? Would he have had the persistence to spend 8 years on the orbit of Mars if he hadn't believed he was uncovering God's geometric blueprint for the universe? Would he have been willing to abandon circles, the most perfect shape, if he hadn't been convinced that the actual shape, whatever it turned out to be, was even more perfect because it was true? I think the answer is that Kepler's mysticism and his science were inseparable. They came from the same source, an overwhelming conviction that the universe was comprehensible, that it had structure, and that the structure could be expressed mathematically. This conviction drove him to look for patterns where others saw chaos. Most of the patterns he found were illusory, a few were real, and the real ones changed everything. Kepler's 3 laws are descriptive, not explanatory. They tell you what planets do, but not why they do it. They tell you that orbits are ellipses, but not why they're ellipses. They tell you that planets move faster when they're closer to the Sun, but not why proximity to the Sun makes them speed up. They tell you that period and distance are related by a specific mathematical formula, but not what physical mechanism creates that relationship. Kepler himself was aware of this gap. He speculated about a force emanating from the Sun, something like magnetism, that swept the planets along in their orbits. He imagined the Sun rotating and dragging the planets with it through some kind of magnetic influence that diminished with distance. This was wrong in its specifics, but remarkably prescient in its general direction. There was a force, it did emanate from the Sun, it did diminish with distance, but it wasn't magnetism. To get from description to explanation, from Kepler's laws to the underlying physics, required someone who could think about force and motion in a completely new way. Someone who could ask not just what path does a planet follow, but what force makes it follow that path. That person was born on Christmas Day 1642 in a farmhouse in Woolsthorpe, Lincolnshire, England. His name was Isaac Newton. But before we get to Newton, I want to pause and talk about the years between Kepler's laws and Newton's explanation, because those years weren't empty. Other people were thinking about these problems, and their contributions, while ultimately overshadowed by Newton, were essential stepping stones. Galileo Galilei, working in Italy, had already begun to transform our understanding of motion. His experiments with inclined planes and falling bodies, possibly including the famous, probably apocryphal experiment of dropping objects from the Leaning Tower of Pisa, led him to the principle of inertia, that an object in motion tends to stay in motion unless acted upon by a force. This was a direct contradiction of Aristotelian physics, which held that objects naturally came to rest, and that continuous motion required continuous application of force. Galileo's insight was revolutionary. In the Aristotelian worldview, you needed to explain why things moved. In Galileo's worldview, you needed to explain why things stopped. Motion was the natural state. Rest or change in motion was what required explanation. This inversion was essential for Newton's later work. Without it, the idea of a planet continuing to move through empty space without being pushed would have seemed absurd. Galileo also turned the newly invented telescope toward the sky, beginning in 1609, the same year Kepler published his first two laws. What he saw demolished the remaining pillars of Aristotelian cosmology. The moon had mountains and craters. It was not a perfect sphere. Jupiter had 4 moons orbiting it, proof that not everything orbited the Earth. Venus showed phases like the moon, strong evidence that it orbited the sun. The sun had dark spots. It was not perfect and unblemished. Galileo published these observations in Sidereus Nuncius, Starry Messenger, in 1610. The book was a sensation. It didn't prove the Copernican system. The Tychonic model could explain most of the same observations, but it made the Ptolemaic system untenable. You could no longer maintain that the heavens were perfect, unchanging, and fundamentally different from the Earth. René Descartes, the French philosopher and mathematician, proposed a physical mechanism for planetary motion, vortices of invisible matter swirling through space, carrying the planets along like leaves in a whirlpool. The vortex theory was elegant, intuitive, and completely wrong, but it represented an important step, the idea that planetary motion required a physical explanation, not just a mathematical description. Descartes shifted the question from geometry to physics. Robert Hooke, a brilliant, combative polymath who would later become Newton's most bitter rival, was thinking about gravity in the 1660s and 70s. Hooke proposed that the planets were attracted to the sun by a force that decreased with distance, and that this force, combined with the planet's tendency to move in a straight line, produced curved orbits. This was qualitatively correct. Hooke even suggested that the force might follow an inverse square law, decreasing as the square of the distance. But Hooke couldn't prove it mathematically. He could state the hypothesis, but couldn't derive the elliptical orbits from it. Edmund Halley, yes, the comet guy, was also working on the problem. In 1684, he visited Newton at Cambridge to ask whether an inverse square force law would produce elliptical orbits. Newton replied almost casually that he had already solved the problem years ago but had misplaced the proof. He promised to redo it and send it to Halley. What Newton sent was not a brief proof. It was the beginning of the Principia. Isaac Newton was born prematurely on Christmas Day, 1642, according to the Julian calendar then in use in England. He was so small at birth that his mother later said he would have fit inside a quart mug. His father, also named Isaac Newton, had died 3 months before his birth. His mother, Hannah, remarried when Newton was 3, leaving him in the care of his maternal grandmother. This abandonment, and abandonment is not too strong a word, seems to have marked Newton profoundly. He grew up solitary, suspicious, and ferociously driven. He later listed in a confessional document his childhood sins, which included threatening my father and mother Smith to burn them and the house over them. Smith was his stepfather, Barnabas Smith, a wealthy clergyman whom Newton despised. When Hannah returned after Barnabas's death, she found a son who was brilliant, angry, and deeply alone. Newton attended the King's School in Grantham and then Trinity College, Cambridge, where he was admitted as a sizar, a student who earned his keep by performing menial services for wealthier students. He was not a particularly distinguished undergraduate. His brilliance emerged gradually, fed by voracious and largely self-directed reading of mathematics and natural philosophy. The legendary period of Newton's early genius is the annus mirabilis, the miraculous year, or more accurately, the miraculous 18 months from 1665 to 1667, when the plague closed Cambridge University and Newton retreated to his family's farm in Woolsthorpe. During this period, he later claimed he developed the foundations of calculus, discovered the composition of white light through prism experiments, and began his thinking about gravity. The famous apple story that Newton was inspired to think about gravity by watching an apple fall from a tree has a basis in fact, though the popular image of an apple bonking him on the head is almost certainly embellished. Newton himself told the story to several people in his old age, including William Stukeley, who recorded it in a biography. Newton said the falling apple prompted him to wonder whether the same force that pulled the apple to the ground might also be responsible for keeping the moon in its orbit. It was a question of remarkable simplicity and profound depth. Is the moon falling? Is it falling toward the earth constantly, the way the apple falls, but moving sideways fast enough that the curve of its fall matches the curve of the Earth's surface, so it never actually hits? The answer is yes, the moon is falling. It has been falling toward the Earth for billions of years. But its sideways motion, its orbital velocity, is precisely sufficient that the rate at which it falls toward the Earth matches the rate at which the Earth's surface curves away from it. The result is a closed orbit. The moon falls forever but never lands. This insight that orbital motion is just falling with enough sideways speed is perhaps the single most important conceptual breakthrough in the history of physics. It unified terrestrial and celestial mechanics. The same force that pulls apples from trees holds planets in their orbits. The heavens are not a separate realm governed by separate laws. There is one physics, one set of laws governing everything from falling fruits to orbiting moons. But insight is not proof. To turn this idea into a quantitative theory, Newton needed to show that an inverse square law of gravity, a force that decreases as the square of the distance between two objects, would produce exactly the elliptical orbits that Kepler had discovered. This required mathematics that didn't exist yet, so Newton invented it. What Newton invented is what we now call calculus, though Newton called it the method of fluxions. Calculus is the mathematics of continuous change. It allows you to describe how quantities change over time, velocity, acceleration, force, position, and to derive precise quantitative relationships between them. Without calculus, the equations of planetary motion cannot be derived. With it, they fall out almost naturally. Newton also needed to formulate his laws of motion, the three laws that form the foundation of what we now call classical mechanics. The first law: an object remains at rest or in uniform straight-line motion unless acted upon by a force. This is Galileo's principle of inertia, formalized and generalized. The second law: the acceleration of an object is proportional to the force applied and inversely proportional to its mass. F equals ma, force equals mass times acceleration. This is the bridge between force and motion, the equation that allows you to calculate how an object moves when you know what forces act on it. The third law: for every action there is an equal and opposite reaction. The sun pulls on the earth pulls back on the sun with equal force. The asymmetry we observe, the earth orbits the sun, not the other way around, is due to the sun's much greater mass, not a greater force. With these tools, calculus, the laws of motion, and the inverse square law of gravity, Newton could do something no one had ever done before. He could start with a physical hypothesis. Every object attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them, and derive mathematically the exact shape of the resulting orbit. And that shape was an ellipse with the sun at one focus, exactly as Kepler had discovered empirically from Tycho's data. This was not just a confirmation of Kepler, It was a transcendence of Kepler. Kepler had described 3 patterns in planetary motion. Newton explained all 3 with a single law. The elliptical orbits, Kepler's first law, follow directly from the inverse square law. Newton proved this using the newly invented calculus, showing that the solution to the equations of motion for a body moving under an inverse square force is a conic section, an ellipse, parabola, or hyperbola depending on the object's energy. Bound objects, planets, follow ellipses. Unbound objects, some comets, follow parabolas or hyperbolas. The equal area law, Kepler's second law, follows from the fact that gravity is a central force, directed along the line between the Sun and the planet. Newton showed that any central force, not just inverse square, produces equal areas in equal times. This means Kepler's second law is actually more general than his first. It doesn't depend on the specific form of the gravitational force, only on its direction. The period-distance relationship, Kepler's third law, follows from combining the inverse square law with the equations for circular or elliptical motion. Newton derived the exact form t squared equals 4 pi squared a cubed divided by gm, where g is the gravitational constant and m is the mass of the Sun. This means that Kepler's third law isn't just an empirical pattern, it's a mathematical consequence of universal gravitation, and it contains a bonus: the constant of proportionality depends on the Sun's mass. This means that by measuring T and A for any planet, you can calculate the mass of the Sun. By measuring T and A for any moon orbiting a planet, you can calculate the mass of that planet. Kepler's third law, interpreted through Newton's physics, becomes a scale for weighing celestial objects from a distance. This is what Newton did. He took Kepler's 3 descriptive laws and showed that all 3 were consequences of a single physical law: universal gravitation. In doing so, he didn't just explain planetary motion, he unified physics. The same law that governs planets governs cannonballs, ocean tides, the precession of equinoxes, the shape of the Earth, the trajectories of comets, and the motion of every object in the universe. He published all of this in 1687 in Philosophia Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. The Principia is widely considered the most important scientific book ever written. That assessment is not hyperbole before the Principia. Physics was a collection of disparate observations and ad hoc rules. After the Principia, physics was a unified mathematical framework that could, in principle, describe the motion of any object anywhere in the universe, and it almost didn't get published. Newton was a man of extraordinary intellectual power and equally extraordinary personal dysfunction. He was secretive, suspicious, vindictive, and pathologically reluctant to share his work. He had made many of his key discoveries years, sometimes decades, before publishing them. The calculus was developed in the 1660s, but not published until much later. His optical experiments were done in the 1660s and 70s, but published grudgingly after Robert Hooke criticized his first paper on the subject. Newton's reaction to criticism was not to engage or rebut, it was to withdraw. After Hooke attacked his optical work, Newton retreated from scientific correspondence for years. He told colleagues he would rather not publish at all than deal with the litigious, his word responses of other scientists. For a man who had solved the deepest problems in physics, he was astonishingly thin-skinned. It was Edmund Halley who dragged the Principia into existence. After Newton mentioned that he had solved the problem of orbital mechanics, Halley recognized the significance and urged Newton to write it up. Newton, once engaged, worked with characteristic intensity. The Principia was composed in roughly 18 months, during which Newton reportedly forgot to eat, slept irregularly, and barely spoke to anyone. When his servant brought meals, he would find them untouched hours later. Newton would stand in his room, thinking, 1 foot raised to put on a shoe, frozen in that position for extended periods as his mind worked through a mathematical proof. Halley didn't just encourage Newton, he financed the publication. The Royal Society, which was supposed to fund it, had spent its budget on a lavishly illustrated book about fish. Halley paid for the printing of the Principia out of his own pocket. If Halley had been less persistent or less generous, the Principia might not have been published when it was, and the history of physics would have been different. The publication was complicated by the inevitable clash with Robert Hooke. Hooke claimed that Newton had stolen the idea of the inverse square law from him, that he, Hooke, had proposed the inverse square law first in correspondence with Newton. There was some truth to this. Hooke had indeed suggested the inverse square law in a letter to Newton in 1680, but suggesting a hypothesis and proving it mathematically are entirely different things. Hooke could state the hypothesis. Newton could derive everything from it. The difference is the difference between saying, "I think the earth is round," and calculating its circumference. Newton was furious. He considered removing all references to Hooke from the Principia. Halley talked him out of this, and Newton grudgingly added an acknowledgement that Hooke, Halley, and Christopher Wren had independently considered the inverse square law. But Newton's resentment was lasting and toxic. He reportedly said of Hooke, "If I have seen further, it is by standing on the shoulders of giants." This is usually quoted as an example of Newton's humility. It was almost certainly nothing of the kind. Hooke was a small man, physically short, and many historians believe Newton's giant's comment was a deliberate, cutting reference to Hooke's stature, implying that Hooke was not among the giants on whose shoulders Newton stood. Newton's combativeness didn't end with Hooke. His dispute with Gottfried Wilhelm Leibniz over the invention of calculus consumed the last decades of his life and poisoned relations between English and continental mathematics for over a century. Both men had independently developed calculus, Newton earlier but unpublished, Leibniz later but published first. The question of priority became a matter of national pride, English versus German mathematics, and Newton, as president of the Royal Society, appointed a committee to investigate. The committee, stacked with Newton's allies, ruled in Newton's favor. The report was largely written by Newton himself. It was not a proud moment for science. But the Principia itself, the actual content, stripped of its human drama, is staggering. Let me walk you through one example that shows the power of Newton's framework, because it illustrates something important about how science works. Newton used his theory of gravity to predict the shape of the Earth. If the Earth were not rotating, gravity alone would pull it into a perfect sphere. But the Earth does rotate, and the centrifugal effect of that rotation is strongest at the equator and zero at the poles. This means material at the equator is flung outward slightly more than material at the poles. The result, Newton calculated, should be an oblate spheroid, a sphere that is slightly flattened at the poles and slightly bulging at the equator. This was a prediction. Newton didn't observe the Earth's shape, he calculated it from first principles. The prediction could be tested by measuring the length of a degree of latitude at different places on the Earth's surface. If the Earth is an oblate spheroid, a degree of latitude should be slightly longer near the poles than near the equator. In the 1730s, the French Academy of Sciences sent 2 expeditions, one to Lapland near the Arctic and one to Peru near the equator, to measure exactly this. The measurements confirmed Newton's prediction. The Earth is indeed oblate. A degree of latitude is about 1 kilometer longer in Lapland than in Peru. This might seem like a minor point, but it's actually profound. Newton's theory of gravity, derived from the motion of planets and moons, could predict the shape of the Earth itself. A theory born from looking up at the sky told you something about the ground beneath your feet. That kind of explanatory reach, the ability of a single law to illuminate phenomena in completely different domains, is the hallmark of deep truth. Newton also explained the tides. The gravitational pull of the moon, and to a lesser extent the sun, raises bulges in the Earth's oceans on both the near side and the far side. The near side because the water there is pulled more strongly toward the moon than the Earth's center, and the far side because the Earth's center is pulled more strongly toward the moon than the distant water. As the Earth rotates beneath these bulges, any given point on the coast experiences 2 high tides and 2 low tides per day. The timing, height, and character of the tides depend on the positions of the moon and sun relative to the Earth, the shape of the coastline, and the depth of the ocean, all factors that Newton's theory could, in principle, account for. He explained the precession of the equinoxes, the slow wobble of Earth's rotational axis that causes the position of the celestial pole to trace a circle against the stars over a period of about 26,000 years. The precession had been known since Hipparchus in the 2nd century BC, but nobody had explained why it happened. Newton showed that it was caused by the gravitational pull of the moon and sun on the Earth's equatorial bulge, the same bulge he had predicted from his theory of gravity and the Earth's rotation. He predicted the orbits of comets. Before Newton, comets were mysterious, appearing without warning, following paths that seemed to defy the regular motions of the planets. Newton showed that comets followed the same law of gravity as everything else. They moved in highly elongated ellipses or parabolas, whipping around the sun and then receding into the outer solar system for years or centuries before returning. Halley used Newton's methods to calculate the orbit of the great comet of 1682 and predicted it would return in 1758. It did, 16 years after Halley's death. The comet now bears his name. Every one of these predictions, the shape of the Earth, the tides, the precession, the comets, flowed from a single law. Every mass attracts every other mass with a force proportional to the product of the masses and inversely proportional to the square of the distance between them. One law, an entire universe of consequences. This is what Newton did. He didn't just solve a problem, he created a framework for solving all problems of a certain kind. Before Newton, each celestial phenomenon was its own puzzle. After Newton, all celestial phenomena were aspects of a single puzzle, and the puzzle had a known solution. Now, let me step back and look at the entire chain, Tycho, Kepler, Newton, because the chain itself teaches something important about how science actually works, as opposed to how we usually imagine it works. The popular image of scientific discovery is the lone genius having a flash of insight, Newton and the apple, Archimedes and the bathtub, Einstein and the thought experiment. The reality is messier, more collaborative and more dependent on accumulated work than the mythology suggests. Tycho Brahe did not discover the laws of planetary motion. He didn't have the mathematical ability, but without his data, Kepler couldn't have discovered them either. The laws were hidden in the data, but you needed both the data and the mathematical skill to extract them. Tycho had the data. Kepler had the skill. Neither alone would have sufficed. Kepler did not explain why the laws were true. He could describe the patterns, ellipses, equal areas, the period-distance relationship, but he couldn't derive them from any underlying principle. That required a new kind of mathematics and a new concept of force. Kepler didn't have either. Newton had both. Newton did not collect the data. He didn't even do significant astronomical observation. He worked from the data and laws provided by Tycho and Kepler, combined with Galileo's insights about motion and his own mathematical inventions. Newton's genius was synthesis, taking pieces from multiple sources and combining them into something greater than the sum of its parts. The chain is observation, pattern, explanation. Tycho observed. Kepler found the pattern. Newton provided the explanation. Each step depended on the previous one. Each required a different kind of genius. And the whole enterprise took 150 years. This temporal scale is important. We often imagine scientific revolutions as sudden events, a paradigm shift, a eureka moment. And sometimes they are, but more often they're generational projects. The Copernican revolution, the shift from an Earth-centered to a sun-centered cosmos, began with Copernicus's publication in 1543 and wasn't fully complete until Newton's Principia in 1687. That's nearly a century and a half. Multiple human lifetimes. Copernicus was dead before Tycho started observing. Tycho was dead before Kepler finished his laws. Kepler was dead before Newton was born. The knowledge was transmitted across generations, through books, through letters, through personal contact. Each generation built on the previous one's work, sometimes understanding it, sometimes misunderstanding it, sometimes deliberately repurposing it for ends the original author never intended. Kepler used Tycho's data in ways Tycho would not have approved of to support the Copernican model rather than the Tychonic one. Newton used Kepler's laws in ways Kepler might not have recognized as consequences of a physical theory rather than expressions of divine geometry. This is how science progresses, not through isolated geniuses, but through chains of transmission, argument, and reinterpretation. The genius is necessary but not sufficient. The data is necessary but not sufficient. The mathematical tools are necessary but not sufficient. You need all of them, arriving in the right order at the right time in the hands of people capable of using them. And you need something else, something that's easy to overlook, but may be the most important factor of all. You need the willingness to be wrong. Kepler spent 8 years trying to make Mars's orbit circular, 8 years of failed attempts. Each failure was painful, not just intellectually but emotionally. Kepler believed in the perfection of circles. He wanted orbits to be circular. His mystical conviction that the universe was built on perfect geometric forms demanded circles. Every failed attempt to fit the data to a circle was a challenge not just to his calculations but to his worldview. And yet when the data insisted that circles didn't work, Kepler listened. He abandoned circles. He tried other shapes. He eventually found the ellipse. This willingness, the willingness to let the data override your beliefs, is the essence of the scientific method. And it is much harder than it sounds. Think about how strong the commitment to circular orbits was. It wasn't just a casual preference, it was a philosophical axiom rooted in 2,000 years of tradition, endorsed by the greatest minds in history and intertwined with religious doctrine about the perfection of God's creation. Abandoning circles meant challenging Plato, Aristotle, Ptolemy, and implicitly the theological argument that the heavens reflected divine perfection. Kepler was a devout Christian. This was not an easy step for him. He didn't take it lightly. He agonized over it. In the Astronomia Nova, he describes his struggle with remarkable emotional honesty. He writes about his frustration, his exhaustion, his moments of despair. He describes ideas that seemed brilliant at 2 in the morning and collapsed by dawn. He describes computational errors that sent him down blind alleys for months before he discovered the mistake and had to start over. And he describes the moment when he realized that the orbit was an ellipse, not with triumph, but with a kind of sheepish astonishment. He had been searching for an ovoid shape, an egg-like curve, and had been computing the distances between his ovoid and the positions predicted by Tycho's data. The errors were small but persistent. Then he realized that the ovoid he was computing was, within his computational precision, an ellipse. He had been looking at the answer without recognizing it. He wrote, "Oh, what a foolish bird I have been." That phrase, "Oh, what a foolish bird I have been," captures something essential about the scientific process. Discovery is not a triumphant march from ignorance to knowledge. It's a stumbling, bumbling, mistake-ridden process in which the discoverer is often the last person to understand what they've found. The data knows the answer before the scientist does. The scientist's job is to stop getting in the way of the data long enough for the answer to become visible. Newton had a different relationship with error. He didn't stumble toward the truth, he derived it. His approach was axiomatic and deductive. Start with a small number of laws, apply mathematics, derive consequences. Compare with observation. If the consequences match observation, the laws are validated. If they don't, the laws need revision. This sounds clean and logical, and in the Principia it's presented that way. But Newton's actual working process was messier than the published version suggests. He sometimes worked backward, starting from a known result and constructing a proof that made it look as if the result had been derived from first principles. He adjusted constants, fudged calculations, and presented results with more decimal places of accuracy than his data warranted. He was not above making his theory look more precise than it actually was. This isn't dishonesty exactly, or at least not the kind of dishonesty that leads to wrong results. Newton knew his theory was correct. He knew the law of gravity was right. He was willing to massage the presentation to make the correctness more persuasive. The modern scientific community would frown on this. Newton didn't care. He was not interested in process. He was interested in truth, and he was right. The theory was correct. The predictions were accurate, stunningly, comprehensively accurate. For more than 2 centuries, Newtonian mechanics was the unchallenged foundation of physics. Every planet, every moon, every comet, every projectile, every machine, all described by Newton's 3 laws and the law of universal gravitation. The Principia was not just a scientific breakthrough, it was the birth of modern physics as a discipline. Let me tell you about the aftermath. What happened to each of these 3 men, because their fates are as revealing as their discoveries. Tycho died in Prague in 1601 at 54, probably of kidney failure. His data, the most valuable in the history of astronomy, passed to Kepler, who spent the rest of his life mining it for discoveries. Tycho's instruments were scattered. Some remained in Prague, some were taken by his heirs, many were eventually lost. His observatory on Heaven was demolished by the Danes after his departure. The islanders apparently delighted to be rid of their tyrannical astronomer landlord. Today the site is marked by a museum and garden. The instruments are gone, the moose is gone, the dwarf is gone, the nose is gone, only the data survives, and only because Kepler took it. Tycho's cosmological model, the Tychonic system, with the sun orbiting the Earth while the planets orbit the sun, was popular for a time, especially among Jesuit astronomers who needed a model that preserved Earth's centrality for theological reasons, but matched the observational data. Eventually, as the evidence for heliocentrism became overwhelming, the Tychonic model was abandoned. Today it's remembered as a historical curiosity, a halfway house between Ptolemy and Copernicus that nobody lives in anymore, but Tycho's data that endures. It was the raw material from which Kepler extracted his laws, and those laws were the foundation on which Newton built his physics. Without Tycho's obsessive, decades-long campaign of observation, the entire chain breaks. Nobody gives Tycho enough credit for this. He is remembered for his nose and his moose. He should be remembered for his data. Kepler's later life was a cascade of hardship that would break most people. His first wife, Barbara, died in 1611. His 3-year-old son died of smallpox the same year. His patron, Emperor Rudolf II, was deposed by his brother Matthias, and Kepler's position became precarious. He moved to Linz, in Austria, where he continued his mathematical work. While struggling with poverty, religious persecution, he was a Lutheran in Catholic territory, and family crises. His mother, Katharina, was accused of witchcraft in 1615, a charge that carried the potential for torture and execution. Kepler spent 6 years defending her, writing lengthy legal briefs and traveling repeatedly to Württemberg to argue her case. The accusation was rooted in a personal dispute between Katharina and a neighbour, but it escalated through the machinery of witch trial hysteria that was endemic in early 17th century Germany. Katharina was eventually released in 1621 after spending 14 months in prison, but she died 6 months later. The ordeal consumed years of Kepler's life that could have been devoted to science. Despite everything, Kepler continued to work. He published the Rudolphine tables in 1627, the most accurate astronomical tables ever produced, based on Tycho's data and Kepler's own laws. These tables were a practical triumph. For the first time, astronomers and navigators had reliable predictions of planetary positions that were accurate to within a few arcminutes. The tables remained the standard reference for over a century. Kepler died on November 15, 1630 in Regensburg at the age of 58. He had been travelling to collect money owed to him. Much of his salary was perpetually in arrears and fell ill on the journey. He was buried in the Protestant cemetery in Regensburg. His grave was destroyed during the 30 Years' War just a few years after his death. His epitaph, which he wrote himself, reads, "I used to measure the heavens, now I shall measure the shadows of the earth. Although my soul was from heaven, the shadow of my body lies here." It's a beautiful epitaph. And it carries a poignant irony. Kepler, who uncovered the mathematical harmony of planetary orbits, spent much of his life in the shadow of poverty, grief, and persecution. The universe he described was orderly and beautiful. The life he lived was chaotic and painful. The contrast is almost unbearable. Newton lived longer than either Tycho or Kepler. He died in 1727 at the age of 84, and his later life was very different from his early years of solitary genius. After the Principia, Newton's interests shifted. He spent decades as warden and then master of the Royal Mint, overseeing England's currency and personally pursuing counterfeiters with a zeal that bordered on obsession. He was elected to Parliament, though he reportedly spoke only once during his tenure to ask an usher to close a window because of a draught. He was knighted by Queen Anne in 1705, making him Sir Isaac Newton, the first scientist to be knighted for scientific work rather than political service. He became president of the Royal Society in 1703 and ruled it with an iron hand until his death 24 years later. He used his position to settle scores, promote allies, and suppress opponents. His persecution of Leibniz over the calculus priority dispute was conducted through the Royal Society's official channels, giving it an appearance of institutional authority that masked what was essentially a personal vendetta. Newton spent more time on alchemy and biblical chronology than he did on physics. His alchemical manuscripts, thousands of pages of notes on transmutation, the philosopher's stone, and arcane chemical procedures were considered an embarrassment by his scientific admirers and were largely suppressed until the 20th century. When the economist John Maynard Keynes purchased many of these manuscripts at auction in 1936, he described Newton not as the first physicist, but as the last of the magicians. Newton also wrote extensively on theology, attempting to date biblical events using astronomical methods and arguing for an unorthodox interpretation of the Trinity that would have been considered heretical by the Church of England. He kept these views largely private. Public heresy would have cost him his position at Cambridge and possibly his freedom. The portrait that emerges is of a man of almost incomprehensible intellectual power, yoked to a personality that was suspicious, petty, vindictive, and deeply strange. Newton could derive the laws governing the motion of every object in the universe, but he couldn't maintain a friendship. He could predict the return of comets, but he couldn't forgive a slight. He was by any measure one of the greatest minds in human history. He was also, by almost every account, profoundly unpleasant to be around. And yet, and this is the part that matters, the work endures. Whatever Newton was as a person, Whatever his psychological quirks and interpersonal failures, the Principia stands. It stood for 2 centuries as the unchallenged foundation of physics. It still stands as a valid description of reality in every context except the extremely fast, where special relativity takes over, the extremely massive, where general relativity modifies the picture, and the extremely small, where quantum mechanics applies for everything in between, which includes virtually all of everyday experience and most of engineering. Newton's physics is not approximately right. It's exactly right. The corrections that Einstein provided in the 20th century, special relativity in 1905, general relativity in 1915, are refinements. They don't replace Newton, they extend him. In the limit of low velocities and weak gravitational fields, Einstein's equations reduce to Newton's. The Principia is not wrong. It's a special case of a more general theory. And that more general theory was itself built on Newton's foundation, using Newton's concepts of force, mass, acceleration, and gravitational attraction as starting points. So when I say these 3 men, Tycho, Kepler, Newton, explained how planets move, I don't mean they had some interesting ideas that were later superseded. I mean they created a framework of understanding that is still used today. When NASA calculates the trajectory of a spacecraft to Mars, they use Newton's laws, augmented with relativistic corrections for high-precision applications, but fundamentally Newtonian. When astronomers calculate the mass of a distant star from the orbit of its companion, they use Kepler's third law interpreted through Newton's physics. When engineers design satellite orbits, they use equations derived directly from the Principia. The ghost of Tycho's data lives in every spacecraft trajectory. The ghost of Kepler's ellipses lives in every orbital calculation. The ghost of Newton's laws lives in every physics textbook, every engineering manual, every navigation system on every ship and plane and spacecraft that has ever traveled. 3 men, 150 years, and they gave us the ability to predict the motions of worlds. Let me talk about something that I think is underappreciated in this story, the role of failure. Kepler's first major work, the Mysterium Cosmographicum, was wrong. The Platonic solids have nothing to do with planetary spacing. It was a beautiful, elegant, completely incorrect theory. Kepler spent years on it, he was proud of it, and it was wrong, but it wasn't wasted. The Mysterium demonstrated Kepler's mathematical skill and brought him to Tycho's attention. Without the Mysterium, Kepler might never have gone to Prague. Without Prague, he might never have gotten Tycho's data. Without the data, he couldn't have discovered the laws of planetary motion. A wrong theory led through a chain of human connections and historical accidents to the right one. Kepler's 8-year struggle with the orbit of Mars was largely a chronicle of failure. Thousands of calculated orbits, each one wrong. Years of painstaking computation done by hand with ink and paper, using arithmetic methods that were crude by modern standards, leading to result after result that didn't match the data. Each failure narrowed the space of possibilities. Each wrong shape eliminated a candidate. The ellipse wasn't found through inspiration. It was found through exhaustion, the exhaustion of every other option. Newton's early attempt to verify the inverse square law using the moon's orbit, what's sometimes called the moon test, initially produced a result that was off by about 15%. This was because Newton was using an inaccurate value for the Earth's radius, which was essential to the calculation. The discrepancy bothered him so much that he shelved the entire project for years. When a more accurate measurement of the Earth's radius became available from a French geodetic survey by Jean Picard, Newton redid the calculation and found excellent agreement. The theory was right all along. He had just been using bad input data. Even the publication of the Principia was in a sense born from failure, or at least from frustration. Newton had been sitting on his results for years, making no move to publish. It took Halley's persistent nagging and the threat that Hooke might publish first and claim priority to finally motivate Newton to write. The greatest physics book ever written exists partly because Newton was annoyed enough at a rival to prove him wrong in public. Failure, frustration, rivalry, stubbornness, hurt feelings, these are the emotional undercurrents of scientific discovery. The clean, logical narrative, hypothesis, experiment, conclusion is a post hoc reconstruction. The actual process is messy, emotional, and deeply human. There's another dimension to this story that I want to explore. The relationship between these men and the institutions that supported or opposed them. Tycho was supported by kings. First Frederick II of Denmark, then Rudolf II of the Holy Roman Empire. Without royal patronage, Uraniborg would never have been built, and the 20-year observational campaign that produced Tycho's data would never have happened. The data that enabled Kepler's laws was ultimately funded by the Danish and Bohemian crowns. But royal patronage is fragile. When political winds shifted, when Frederick died and Christian IV proved less sympathetic, Tycho's entire operation collapsed. The instruments were packed up. The island was abandoned. 20 years of institutional continuity vanished in months. Science funded by the whims of monarchs is science that can be defunded by the whims of monarchs. Kepler, despite his title of imperial mathematician, was perpetually underfunded. The Holy Roman Empire was financially strained by the 30 Years' War, and Kepler's salary was frequently in arrears. He spent significant portions of his intellectual energy on commissioned work, horoscopes for noblemen, calendars for cities, to supplement his income. The man who discovered the laws of planetary motion cast horoscopes to pay his bills. Kepler's relationship with astrology is complex and worth a brief digression. He didn't believe in astrology in the simplistic sense. He didn't think the stars determined individual fates, but he did believe in what he called a reformed astrology, the idea that celestial configurations influenced earthly events through some kind of physical mechanism, perhaps related to the same harmonies he saw in planetary orbits. He was, in modern terms, a scientist who hadn't fully disentangled empirical investigation from mystical speculation. The boundary between astronomy and astrology was not sharp in the early 17th century, and Kepler lived on both sides of it. Newton's situation was different. By his time, science was becoming professionalized. The Royal Society, founded in 1660, provided an institutional framework for scientific communication and validation. University positions. Newton held the Lucasian Chair of Mathematics at Cambridge, provided stable funding. The Principia was published under the auspices of the Royal Society, giving it institutional prestige. But even Newton depended on patronage of a sort. His later career at the Royal Mint was a government appointment. His knighthood was a political reward. His authority at the Royal Society was maintained through networks of influence and favor. Science was becoming institutional, but it hadn't yet achieved the full independence from political and social power that it would claim never fully achieve in later centuries. The story of Tycho, Kepler, and Newton is also a story about the geography of knowledge. Tycho worked in Denmark and Prague. Kepler worked in Austria and Germany. Newton worked in England. The knowledge they produced traveled across these boundaries through books, letters, and personal contacts. But the travel was slow and uncertain. Books took months to reach their readers. Letters could be lost. Translation was imperfect. The scientific revolution was not a single event in a single place. It was a distributed process occurring across multiple countries, in multiple languages, over multiple generations. The fact that it cohered, that Kepler's laws in Germany connected to Newton's physics in England, that Tycho's data in Denmark fed into Kepler's mathematics in Austria, is partly due to the men involved and partly due to the emerging infrastructure of scientific communication, journals, societies, correspondence, networks, universities. This infrastructure was new and fragile. It could have failed. If Kepler's books had been suppressed by religious authorities, and some were temporarily, Newton might never have learned of the three laws. If Newton's Principia had not been published, and it almost wasn't, the mathematical framework connecting gravity to orbits might have been delayed by decades. Each link in the chain was contingent, each could have broken. That it didn't break, that the knowledge passed from hand to hand across generations and borders, accumulating and strengthening as it went, is something close to a miracle. Not a supernatural miracle, but a human one. The miracle of people caring enough about understanding the universe to write things down, share them with strangers, and build on each other's work even when personal relationships were difficult, funding was uncertain, and the practical benefits were unclear. Let me now take the longest possible view. What did these three men actually accomplish, seen from the perspective of 4 centuries later? They accomplished the first successful example of what we might call the scientific program, the project of understanding the natural world through systematic observation, mathematical description, and physical explanation. Others had attempted pieces of this before. The ancient Greeks had observed and theorized. Medieval Islamic astronomers had refined observations and challenged theories. But the complete cycle, observation leading to description, leading to explanation, with each stage rigorous, quantitative, and testable, was achieved for the first time in the story of Tycho, Kepler, and Newton. And the method they demonstrated, their method, arrived at through struggle and accident rather than conscious design, became the template for all subsequent science. Every field of modern science follows at some level the same pattern. Observe, find patterns, explain the patterns with deeper principles, test the principles against new observations, repeat biology. From Linnaeus's classification to Darwin's natural selection to Watson and Crick's DNA follows this pattern. Chemistry, from Lavoisier's elements to Mendeleev's periodic table to quantum chemistry, follows this pattern. Geology, meteorology, medicine, psychology, all of them, to varying degrees, follow the pattern that was first demonstrated in the explanation of planetary motion. This isn't to say that Tycho, Kepler, and Newton consciously invented the scientific method. They didn't. The scientific method as a formal concept was articulated later by Francis Bacon, René Descartes, and others, and in practice, science is far messier than any formalized method suggests. But the story of planetary motion is the first clear, complete, undeniable example of the method in action. It's the proof of concept for the entire scientific enterprise, and the power of that enterprise, the sheer, terrifying, magnificent power of understanding nature mathematically, became apparent almost immediately. Within decades of Newton's death, his methods were being applied to everything from bridge design to ballistics to navigation. The Industrial Revolution, which transformed human civilization in the 18th and 19th centuries, was built on Newtonian physics. Steam engines, textile machinery, railways, telegraphs, all designed using principles derived from or compatible with the Principia. The space program, which I talk about often on this channel, is a direct descendant of Newton's work. When we calculate the trajectory of a rocket, we use Newton's second law. When we design an orbit, we use Newton's law of gravity. When we plan a gravity assist maneuver using a planet's gravity to change a spacecraft's velocity, we use Newtonian orbital mechanics enhanced by the computational power that Newton could only dream of. The Voyager probes now in interstellar space, the Mars rovers rolling across an alien landscape, the James Webb Space Telescope orbiting the Sun at the second Lagrange point. Every human artifact in space, every satellite, every space station, every probe is there because three men over 150 years figured out how gravity works. Tycho measured, Kepler calculated, Newton explained, and we inherited a universe we could understand. There's one more thing I want to say about this story, and then I'll let you go. The three men in this story were not saints. Tycho was a tyrant who bullied his tenants and kept a dwarf for entertainment. Kepler was obsessive to the point of madness, and his mystical convictions led him down as many dead ends as productive paths. Newton was vengeful, secretive, and quite possibly the most difficult person in the history of English science. But they were also, each in their own way, magnificent. They dedicated their lives to something that had no practical value in their own time. Nobody needed Tycho's star catalogue. Nobody needed Kepler's ellipses. Even Newton's Principia, for all its eventual practical applications, was written not for engineers but for philosophers. These men pursued understanding for its own sake, driven by curiosity, ambition, faith, stubbornness, and a conviction that the universe was worth understanding. That conviction is not universal, it's not even common. Most people in most eras are content to take the universe as given and get on with the business of living. The impulse to look up at the sky and ask, why does that move that way? And then to spend a lifetime trying to answer the question is rare and strange and precious. These three men had that impulse. They followed it through poverty, exile, illness, bereavement, persecution, and isolation. They followed it despite opposition from religious authorities, academic rivals, and their own families. They followed it without knowing where it would lead, without assurance that it would lead anywhere at all. And it led to the laws of nature, the actual, genuine, mathematically precise laws governing the motion of every object in the universe, laws that have been tested billions of times and never found wanting within their domain of applicability, laws that let us send robots to other planets and bring samples back, laws that let us predict eclipses to the second centuries in advance. The distance from Tycho's brass quadrant on Heishvan to a SpaceX Falcon landing on a drone ship in the Atlantic is not as far as you might think. It's a straight line, a line of observation, pattern, explanation, and application. Each point on the line was placed by a human being who couldn't see the end of the line but placed their point anyway. That's what science is, not a method, not an institution. A line of people stretching back centuries and forward into an unknowable future, each one placing a point and trusting that someone someday will connect it to the next. Tycho placed his point, Kepler connected it to the next. Newton drew the line through both and extended it further than anyone thought possible. The line continues. It always has. I hope it always will. Thank you for listening tonight. Whether you came for the noseless Dane, the mystical German, or the difficult Englishman, I hope you leave with something more, a sense that the universe is comprehensible, that the comprehension was hard won, and that the people who won it were exactly as flawed, as brilliant, and as stubbornly human as you and me. The planets are still moving. They move in ellipses. The sun sits at one focus. Equal areas are swept in equal times. The square of the period is proportional to the cube of the distance. And all of it follows from the fact that every mass in the universe attracts every other mass with a force that falls off as the square of the distance between them. Three men, 150 years, one law, good night.